Hello, everyone. Thank you for joining this seminar series organized by the Empathic Computing Laboratory. I'm your host, Aladdin, and our guest speaker for today is Makoto Miyakoshi, who is currently a postdoc or assistant professor at UCSD.
I'm what is the name? Assistant project scientist.
Assistant project scientist at UCSD. His research interests are in EEG and everything about the brain. His talk of he's famous for his SCCN Wiki page, the Makoto preprocessing pipeline, which we are using it here in the lab. The title of the talk is "I See Another Solution: Revisiting My Predictions After 5 Years." The talk will be roughly an hour, followed by a brief question and answer session. Thank you for joining us, Makoto.
Thank you very much. Thank you for giving me an opportunity to talk about my slides today. I'm Makoto. As you know, Aladdin introduced me. I'm a project scientist. So project scientist is one level above the postdoc in UCSD terminology. And my background is my PhD is in psychology. So technically I'm a psychologist, but I have been doing this somewhat computational side of the particularly research using EEG, but I also have experience in MRI, fMRI. So I do both MRI and EEG. So I've seen those two cultures. So some of the observations I made is based on such, seeing two different worlds. So today, let me share my screen first. Today I will talk about, all right, desktop 2. Today I'll talk about this I see another solution, blah, blah, blah. It was actually originally the wordplay. The original title 5 years ago was I see a solution. And that relates to the resonate with the independent component analysis, which is the algorithm Scott Makeig, my mentor and the director of the Swartz Center, has applied to the EEG analysis in 1996 for the first time. And he obtained surprisingly good results. And later in the middle 2000s, he developed physiological interpretation of ICA on EEG. And basically he made a really strong claim, which is when you apply ICA on the scalp recorded data, then you got somewhat, closer representation of the ground truth of the EEG. And he, listed and demonstrated the evidence of that. And I think majority of that part of his discussion is still valid today, but here I'm, after 5 years, I'm not simply advertising his claim anymore, but I'm more critical. But still, I think this is majority of the part is valid. Okay, so let me start with that. So when you see the background white, then that is from 5 years ago, and when you see the black, then that's the updated part. Part 1, the future of EEG and Makoto's pessimism. By the way, my bachelor's degree is in Western philosophy, so that's completely different from my PhD. So, but you probably see the taste of that philosophy there. So, as this talk was originally prepared for the BCI researchers and engineers, I chose this topic as an introduction and opening the discussion. By the way, I accept any real-time interruptions. You cannot, you don't even need to ask me to interrupt. You can just interrupt and ask a question or no. It's totally welcome. Okay, so typically the goal of the BCI researchers is to read the complex mind. Like, is he stressed? Is he angry? What is his emotional states? What is he thinking about? Is he going to buy this product or not? You know, this kind of mind reading is one of the ultimate goal of the brain-computer interface, right? So let's do some simple thought experiment. The key question is, does EEG have capacity to represent the complexity of mind? And in this movie, the animation, I'm showing one of the scenes from the Ghost in the Shell in 1996. By the way, 1996 is coincidentally the year my mentor Scott Makeig published ICA EEG paper for the first time. So this Ghost in the Shell, it's the same as the movie Matrix, but you know, your brain and the computer is directly, probably electrically connected, so that brain and the computers are, you know, very smoothly connected, and there is a really thick bandwidth to communicate. So it's not like, oh, we detected the imaginary hand movement on the right hand or left hand. You know, that's like a 2-channel on-off switch. So that's very primitive, right? But in this kind of direct connection, we imagine that this the communication between the brain and the computer is more smooth and more information. Well, let's ask that with, in the case of Scalp recorded EEG, okay, I'm not talking about anything else at this moment. I happen to have this high density EEG recording data, like 256 channel EEG. Again, this is recorded from the Scalp, okay? And I applied a very simple standard engineering process to compress the data using principal component analysis to get 95% of the variance. And how many principal components did I need to obtain the 95% of the EEG data? And that was only 9. And I was shocked. I thought, oh, there must be a mistake in my calculation. But in the MATLAB code, there is only 1 line. So no way to, to make a mistake here. So my original question was, does EEG has capacity to represent the complexity of the mind? And the number is 9. And I gave this talk in Germany, and in German, 9 means no. So this number automatically means no. Very simple. And I thought, okay, what about the case of the ECOG? ECOG is an electrocorticogram. So you implant the electrodes directly on the surface of the brain, or maybe dura, I don't know technically, but it's under the skull, okay? And I happen to have this data as well. And I did the exact same operation, like using PCA to obtain the 95% of the variance, and I got 78. I'm using almost half number of the electrodes, but I got almost 9 times more number of the principal components. And I was very shocked. And this I've never heard of anyone talking about this, but it looks like the conclusion is Scalp recorded the EEG has really limited information, and that information is somewhat lost when this signal goes past the skull and the scalp and those layers. And when I gave this talk, later my colleague told me, oh, that was probably because you were analyzing the uncleaned raw data. And I said, fine. And I asked my colleague to take a look at this. And he used now 740 data sets. So that's not like anecdotal, but it's a good number of the data sets. And he confirms that about 90% of the variance is explained by the first 10 principal components. So my initial estimate of 9 is not too far, because this group level analysis showed 10. And this is after cleaning. So this does not include huge eye blink or anything like that. Well, so one technical question is, okay, why is the scalp recorded EEG so poor in terms of the amount of the information? And this is basically the result. And the answer is the spatial averaging caused by this layer of biological tissues, which is cerebrospinal fluid, scalp. These layers have point spread function, and that point spread function causes the irreversible loss of the information. So once this is mixed, there is basically no way to unmix it. Although as I will mention this later, ICA is kind of a solution to make it possible. In that sense, ICA is a very interesting method. But again, once this is mixed and smeared, then you cannot undo it. So part one, summary. So Makoto's pessimism is basically scalp recorded EEG data has massive dimension reduction already performed by these natural layers of the tissues. And so that even if you have 100 or 10,000 or 100,000 of electrodes, you may not get that much increase of the information from the brain. So if you want to obtain the information from the brain more efficiently, dramatically more efficiently, then you have to implant the electrodes under the skull. That seems the only good solution. And I still think so, basically. Although, I will show you in the next slide, I may find a better solution now. But basically, Makoto's pessimism here means scalp recorded data does not carry that much information in terms of the variance, at least. Okay. And later, after thinking about these things, I became curious about other methods, because I joined Swartz Center, and Swartz Center has been advocating the use of ICA. So I was very eager to disseminate ICA and studying ICA. But after this, I thought maybe we should try other methods. And I came to this book. This is an Electric Field of the Brain by Paul Nunez and Ramesh Srinivasan. And these guys proposed, seemingly very reasonable solution. And it was way before the use of the ICA. So I'm now looking into this solution, which is basically the spline Laplacian or male-born dural imaging, if you have more than 64 channels. But I'm not going to this topic in detail today. Okay, part two. Part two, I will talk about the present of EEG, which is the vacation of the ground truth and address science. And address science is a pseudo word. There is no such a word. I just made it up. And this is my favorite quote from poet, one of the Japanese poets. The soul of a true poet predicts the past and remembers the future. And I didn't understand, although I found it interesting, but I didn't understand what he means by this. But later I will show you one example of this strange paradox. Okay, now when we talk about the potential of EEG today, then that's equivalent of asking what can EEG do today. And back in the 1940s, this Crawford Sams is a brigadier general in occupied Japan. So Japan lost the war against US. And this was the guy who came to occupied Japan as a top of this health science section. And he proudly said, the United States have penicillin and EEG recorder. So he was so proud of this EEG science of the time. Although on the right, I show the journal Brain. We still have that journal today, right? And one of the earliest EEG studies by Adrian and Yamagiwa, and Yamagiwa was actually a Japanese guy, and this was published in 1935. So Japan, some Japanese guy was involved in one of the earliest EEG studies. So this is the pretty technical part of what I do in my work. So as I said, this Swartz Center for Computational Neuroscience has been making own paths by using the ICA and developing ICA related theories and applications and stuff. So I can show you how ICA can be used in these examples. In the left plot, this is what we call the envelope topography analysis. So here is the envelope of the time domain, the EEG potentials, but these are not ERPs, but these are event-related envelope. So envelope is the, showing the maximum and the minimum values, and maximum minimum of what? And it is actually the maximum and minimum of the scalp topography. So this envelope shows the max and min values of all the scalp values, okay? And each independent component can be, can have its own contribution, which can be decomposed into a single frame. So for example, in this envelope topography analysis, the leftmost independent component, which is from the right primary motor cortex, explains as much as 45% of the percent variance accounted for. So which is basically the power ratio, okay? So that means during this 30 to 300 millisecond time window, this independent component explains 45% of the power. So that's non-trivial, right? So that's almost like half of the EEG phenomenon between this time is dominated by this guy. So that gives us a good reason to focus on this independent component as a primary and most dominant during the time. And we can sort that independent component in descending order so that we can discuss what's the second most important independent component in terms of the variance, and this is the guy. And what's the third most important? This is the guy. And we can also talk about where is this guy from, and you can see this localization. This localization is also generated by ICA alone. You do not need to do any other things. This scalp topography itself is the property of ICA. And if you see this nice spatial separation also, the primary motor is from here and primary sensory is from here. And these are spatially almost overlapping, right? But independent component analysis obtains the temporally maximally independent time series. That means although this source and that source are spatially very close to each other, in the time domain, they look very different. Theoretically, they are independent. So that's the power of ICA. So that's very convincing, right? And you can also generate this kind of figures just by running EEG lab. So this is why the novice users and newcomers to the EEG science find EEG lab so attractive, and also the use of the ICA kind of justified in this way. We can also apply that to the group level analysis in this way. And the idea is the same. You can see the envelope filled in, which indicates the independent component activity of this location and in this time domain. So there is always this time domain, spatial domain combined, nice visualization. And you can also evaluate who is most important. So out of this, this guy, 34% is most dominant, and its peak is about here, blah, blah, blah. So this is a very standard way of using ICA. Demo 2, this is more like updated. You cannot find this kind of analysis or studies in the middle to late 2000, but you need to wait until like 2010s at least. So this is one of my first application of group level multivariate Granger causal analysis. So, let me play this movie. Now this is hitting latency 0. And in this movie, latency 0 is a moment of visual cue. And when the subject sees a visual cue, then they make an eye blink. Okay, so this is an eye blink cue. And this movie is a result from the subtraction between tic patients. So tic is a clinical condition in which your facial twitches cannot stop, and that kind of tic patients minus control subjects. So this is already a group difference. Okay, now we start from latency 0. Okay, so now we are hitting about 180 milliseconds. You see a huge information flow from the occipital lobe to the frontal lobe. This means the tic patients have excessive amount of information flow from the occipital to frontal. And our interpretation is, it's not surprising that occipital lobe is, responds to the incoming stimulus, because they are perceptual processes, right? So those perceptual processing guides should be responsive, yes. But if this data says tic patient sends excessive amount of this information flow to the frontal lobe compared with the control, then that may be related to the pathology, right? This is what's going on in the brain. Let me see that more. And this hypofrontal and hyperoccipital activation pattern continues. Oh, excuse me. Oops. What did I do? Sorry. So this pattern continues, all right? Oops. Oh, I missed it again. Sorry. Kind of difficult to use. Oh, okay. Here. Okay. Now you see this point at around 300 and maybe 80 milliseconds. This frontal lobe is responding back to the occipital. So there is that time resolution. So again, up to like 350, 60 millisecond-ish, there is a massive occipital information flow bombarding this frontal lobe. But this frontal lobe responds back a little bit at around this point. But that's not big enough. So this is dominated again from the occipital. So we published this as an evidence of finding some pathology in the tic patients. So this group level source information flow toolbox, SIFT, is what I developed for this project for Sandra Lu from UCLA. And you can, of course, see the same thing in time frequency domain. So movie is most useful to see the temporal development of this 3D spatial thing. So you actually see 3-dimension plus time plus time frequency. So this is a 5-dimensional data presentation. So that's like one of the cutting edge EEG analysis today. But let me talk about the limitations of the EEG analysis, because I don't want to just say, oh, EEG is great, let's do EEG, period. That's like a very one-sided claim. As an EEG researcher, I want to raise a caution about, number one, the limitation of no sensitivity to the basal ganglia. So if you use fMRI, then you can discuss emotion, reward system, whatever. Because these, fMRI sensitivity is not restricted to the gray matter. If there is a bold signal increase in midbrain, then we can detect it. But in the case of EEG, because the generator of the EEG signal is usually limited to the gray matter, if there is no gray matter, then we cannot, measure it, even if that part is activated in whatever ways, as long as they do not have EEG measurable cytoarchitectures, which is simply put, the neurons aligned in parallel, massive parallel structure like this. And it has to be really broad, like several centimeters square. We cannot find such a specific structure in those deep nucleus, including basal ganglia and the thalamus. And also the cerebellum does not have such favorable EEG favorable cytoarchitecture either, so we cannot measure them. So that's a well-known, limitation. Although sometimes people argue, "Oh, we detected something in the thalamus using, EEG," and that's basically, you shouldn't take it literally. Another limitation is that this is a little bit more advanced, but sometimes people use the so-called advanced source imaging or source localization. But those source localization always requires the head model. Head model means here is the shape of the brain. Here is the shape of the cerebrospinal fluid. Here is the shape of the bone. Here is the shape of the scalp. But we do not know the electric conductance of those each tissue. And there are studies showing that there is a huge individual differences in those electric conductivities. And currently there is no way to measure the individualized electric conductivity parameters without taking the real tissue, like a biopsy but we have never heard of biopsy for the purpose of EEG source localization, right? That kind of spoils the merit of non-invasive EEG measurement. So some people misunderstand this issue. They say, "Oh, because we have 7 Tesla MRI, our source localization is great." No, because MRI does not measure the electric conductivity of those tissues. Another issue is those blood vessel structures are completely omitted from the conventional head models, and there is some interesting young guy, Fidera, from some European country, maybe he's from Germany. He studies the effect of the presence of this blood vessel in the brain. So if you use MRI, a spin label method can give you this nice, blood visualization. But again, because we don't know the exact electric conductivity of those blood vessels, that makes the problem even more complicated. Even more fundamental problem here proposed by the author of this big book is that why do even people believe that EEG source is localizable? This is actually a really strange claim. But I will not go into this problem too deep this time. But I just want to mention that EEG source is localizable is actually a claim without a strong support. Okay. Here is another more pessimistic thing. If you see the Wikipedia, actually you can see this picture. So I just took it from the Wikipedia, and I bet that 99.9% of the EEG researchers have never heard of this even. I realized that this could be an issue simply because I was working with a radiologist, and I had a discussion with my colleague radiologist, and they said, "By the way, Makoto, have you thought of the blood vessels that goes into the skull?" And I was like, "What are you talking about?" And he said, "Well, sometimes there is a blood vessel going into the skull. So that means you have holes in the skull," which I have never heard of, But apparently Wikipedia says, yes, there are those holes. And, it's called a foramen. And there are more than one place you have. And you can easily imagine if you have a hole in the skull, then that changes the electric conductivity, right? There is an increased electric conductivity around those holes. And the same guy, Lucas Federer, actually discussed this issue in his PhD thesis. So he's really definitely a smart guy, right? And this is a study from old Japanese health-related research. And I have no idea why this guy, Mr. Kitazawa, wanted to study this population distribution of the foramen holes. But the result is shocking for me, at least, because he found at least 5 patterns in this population of 100 or 200, I forget. It's about, yeah, about 200, right? There are 1 hole, 2 holes, 3 holes, 4 holes, and no hole. And when you say 2 holes, that does not necessarily mean 1 left, 1 right, but sometimes 0 left, 2 right. So this distribution in the left and right hemisphere is not necessarily symmetrical. And if you have 3, you cannot be symmetrical, right? Maybe one of the side has 2 and the other side has only 1. So this is completely random. And this kind of anatomical details of non-interest significantly affects the EEG measurement. So no matter what great resolution your MRI have, if you miss these holes, then that can, generate a huge error in your estimation. And by the way, this Lucas Federer kindly told me that in order to study the effect of this foramen, he needed to use 7 Tesla machine. And he said 3 Tesla, 4 Tesla machine is not good enough to study this hole. So I was really shocked. Okay, so far I have reviewed the technical limitations, which is more or less known to everybody. Some of those topics I covered are less known, so that's like a new topic. But actually I want to raise even more serious, and actually this is probably the most serious issue, which is the vacance of the ground truth. In the case of the MRI studies, we always use phantom, which is filled with the bottle filled with some solution, and we put it in the scanner and we scan it, and you got the image in your screen. So in this case, the ground truth is the phantom in the scanner, and in your screen you got the image of the ground truth, right? Because this connection is guaranteed by the MRI technology, if you find some suspicious point in your image, then you can safely assume that the same issue should be there in your phantom. Or in the case of the clinical practice, if you see some cancer in your image, then you can say that okay, this patient has a cancer here, right? So this correspondence is really firm. My point is that, do we have the same corresponding structure in EEG? When we find something, well, if it's like a very obvious, like here is a big cancer in the brain and that causes epilepsy, and that, the focus of the epilepsy can be localized by using whatever, even the simplest method of the source localization. Yeah, that's like an easy case. But in many cases, for example, cognitive studies, we discuss, this brain pattern should come from motor cortex or occipital cortex and blah, blah, blah. But that's like very vague relation, right? We are talking about front or back or left or right or top or bottom, not like this gyrus or that gyrus or this sulcus. And if we want to focus on this smaller spatial scale, then we run into this problem. Is this 1 centimeter off or 2 centimeter off or 3 centimeter off? Everything at this level is probabilistic, and we cannot say this is a ground truth. So the fundamental skepticism here is I know how to use those signal processings, and there are so many ways to generate these colorful figures from this 1D time series data. And I'm kind of a specialist in doing that. So I know a whole bunch of those tricks, okay? Now, my question is, are we using those colorful methods to approach to the ground truth better? Or are we doing this because we don't have the ground truth? So we are trying to escape from the vacance of the ground truth. If you see the colorful figures, you feel you got convinced, like, oh, okay, wow, this is great, blah, blah, blah. But are we ever become closer to the ground truth? What is the ground truth from the beginning? These fundamental questions are missing. That's how I feel. And why is that the very typically the situation for the EEG? Well, my answer is, this is my thought, but the measurement, the nature of the measurements are different, right? So, for example, in the case of magnetic resonance imaging, you can do the MR microscopy, and the image you see here is an apple seed, and apple seed is so small like this. By the way, apple seed is also the title of another comic by Masamune Shiro, who wrote The Ghost in the Shell, but that's a joke. But here they used 50 micrometer isometric voxel to scan the apple seed, and you can see this whatever this structure inside. So as you increase the magnification rate, then you began to see those smaller spatial structures. That is guaranteed in the case of MRI. Is this also the case in the EEG? That's the real question, and my answer is unfortunately no. We have already seen the Makoto's pessimism, which is even if you have 10,000 EEG electrodes on scalp, you will not get good increased amount of the information. Same applies here. According to this book, in order for the scalp EEG measurement to pick up any brain activity, that activation size in the brain cortex should be at least 1 square centimeter, 1 square inches, which is about 6.35 square centimeters, which is pretty big like this, right? And any brain activation generated by the cortical activation smaller than that area is all neglected. It's like trimmed, and it doesn't come up to the surface. So that's the fundamental limitation. And because of that, we are seeing like filtered results. The scalp recorded EEG is already filtered by this biophysics of EEG, volume conduction. And if you see the website of the SPM, the SPM, the statistical parametric mapping by the Carl Friston's lab in the UCL, there is a SPM history page, and they proudly said the SPM can be thought of as an X-ray of the effect's significance. And I truly envy them for reporting this X-ray analogy with confidence, because that's exactly what we want to have and what we can't in the case of EEG. So this lack of the ground truth in EEG is the most serious problem of EEG, although many EEG researchers have never thought of that. So that's a problem in many ways, right? Number one, this problem is by itself a serious problem. But number two, the social situation in the EEG researchers, the people's indifference in this fundamental problem is another issue. So it's multiply a problematic. And here I want to also point out this issue, which I often noticed as I start to work with Swartz Center. People easily got confused with good engineering and good science. And from my viewpoint, of course, this is for the sake of the argument, okay? I'm not trying to say engineering is lower and science is higher, but I'm trying to say there is a distinction, okay? So this bring us back to the one of the fundamental questions of what is science and what is science for, right? So this Norwood Hansen is he was a philosopher, but also he was a pilot in World War II. So he was called a flying professor. And his background was actually the physics. So his book talks a lot about contemporary physics, like Einstein's relativity theory, etc., from the viewpoint of the philosophy of science. And he said the distinction, well, this is not what he said, but he said the theory ladenness in observation is what makes science science. And this theory ladenness means you always have to have some prediction. And without a prediction, even if you see some phenomena which is potentially very important, you cannot get its meaning. And you can only realize the importance of or meaning of the phenomena if you have prediction. And this prediction is, in his term, is called the theory ladenness. So I think his remark here resonates with what Marcel Proust said. He said the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. So you have to have new eyes. And this new eyes basically means you have to have top-down prediction, and that is the theory-laden observation in eyes, right? So if you have the same eyes but with different theory-ladenness, then you can find something different. Yeah, I'll skip that. Okay, so EEG as an address science. So I want to say currently EEG is in between science and engineering and something else. Sometimes I even find pseudoscience in EEG, like, oh, this is, this brain pattern is resonating with other, other people, or this is a resonance with even some spiritual things. These are all pseudoscience, but because EEG lacks really strong support, like MRI-based science is supported by physics, because electromagnetic theory is established, and once they start some discussions, then they always come back to that firm ground of theory. And EEG, unfortunately, does not have that. And the facts confirmed in the EEG is almost all empirical, and it does not have a real strong theory, unfortunately. So, and people's mentalities are also immature in my observation. That's why I call it the address sense of the science. So I combined the word again, and I made the word address science. Okay, so that's the summary. So I wanted to confirm that the lack of the ground truth in the EEG is a problem. And, to make this argument more like trackable, I want to point out that the generator of the EEG is the neurons. That's the confirmed fact. And that's the firm ground we can stand on, at least. And there are types of the neurons. For example, if the neuron has this long leg, and maybe that may be supported by this horizontally spreading patterns, but what we measure is this part, the electric current generated by this part of the structure. That's what we measure, not necessarily those entangled complex part. So sometimes we have to go back to these neurons as a real ground truth holder of the EEG, and always reconfirm what it means in terms of the neurons language. even if that seems sometimes a very long path to go. Typically, EEG researchers simply means EEG end users, and they skip this basic part, and they based on other studies. So this is a relative references without having a real solid reference. So if you read this electric field of the brain, this was written by physicists for the first time in history of EEG. And this Paul Nunez is actually living over there by 20 minutes by car. So I often see him for discussion. And I have enjoyed having discussion with him in the weekend in the past couple of years. So I want to become a good student of him. He's a retired professor. And he did a lot of very important works in the EEG. Let me introduce some of the most important works he did. So this is one of the famous experiment in the physics. And this is just a plate and combined with an oscillator. And now you enter the oscillation frequency and solve. And you use this tone generator, which is a simple sinusoidal waves. Then you see these patterns appear. So this is called the Klandny figures. And this was found in the 17th century even. And as the frequency goes up, this pattern becomes more spatially finer and finer. See, this is more finer pattern, smaller spatial scales, like higher spatial frequencies. Hold on, someone is knocking. Oh, hey, sorry. Okay. Thanks. So you might wonder what does this relate to EEG? And Paul Nunez is saying that actually the same thing is happening in the brain. Brain, I can say that it's in the brain. And you might have heard of this resonance in Earth. This is called a Schumann resonance. So there is a lightning bolt in somewhere in the Earth. And this there is an air layer here, right? And this layer of the air forms the cavity, and that makes a resonance. And because there is always like 50 thunderbolt per second somewhere on the Earth, is happening constantly, and there are like 2,000 the storm of the rains somewhere on the Earth. So there is always this lightning bolt. So that generates the constant resonance of the Earth, which has, interestingly, the central frequency of about 7.8 hertz. But the exactly same thing is happening in head, which is one of the most under-evaluated but potentially most important prediction made by the very solid physicist who wrote this book. And I wanna study this thing more, and it's very fundamentally important in my idea, in my understanding. Okay. I'll skip that. Part 3, Popperian defense and cul-de-sac. I will explain what this is later. By the way, my graduate thesis was about Friedrich Nietzsche. I read one of his books and wrote graduate thesis. My mentor was a specialist of the Meister Eckhart, which is a German mysticism guy. So here is the one-page history of EEG and ERP from the viewpoint of postdoc from Japan to UCSD in 2017. So this is Caton, who studied the animal ECOG in 1875. This is really amazing. And he's from UK. And later, about 50 years later, this is Barger. We all know Barger. He found alpharism, and alpharism is sometimes called a Bargerism after his name. And he's from Germany. And Davis, he reported the first ERP papers, and this guy is from UK. And this Davis mentored Galambos. Galambos is a mentor of the Scott Makeig, and Scott Makeig is a mentor of me. So in a sense, this Davis is my grand mentor. But my point is that this is a UK, Germany, UK, and Harvard, because he studied in the UK and he was from Harvard. So he brought EEG research back to Harvard, East Coast. And Galambos, this guy, was in Harvard, but he moved to West. So he brought this EEG research from East Coast to West Coast. And he mentored a couple of famous people here. He is Stephen Hilliard, and this is Stephen Luck. He is the mentor of this guy. So the University of California, San Diego, he studied the neuroscience department. Since then, this UCSD has produced a lot of good EEG researches. But let's get back to that critical question again. What is science? And I mentioned that science requires a top-down, the theory-laden eyes, blah, blah, blah. And this Karl Popper, he is also pretty famous for the discussion of what is science. And he has a very clear definition of science that is a falsifiability. If some claim cannot be falsifiable, then that's not science. That's a very famous and very often quoted his statement. But without having that philosophical look, let me summarize his claim in an engineering way using the chart, okay? Hypothesis, question, and experiment. And if that result from the experiment is supports your hypothesis or not supports the hypothesis, now you got 1 or 0. And of course, the real phenomena is not that black or white. That's why we use statistics, and that's why we use 0.05 as a cutoff value, right? If something shows p-value smaller than 0.05, then yes, hypothesis supported. But if it's 0.06 or 0.08 or 0.13, blah, 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 larger than 0.05, then hypothesis not supported, typically, okay? In terms of the inferential statistics, the null hypothesis must be rejected. And null hypothesis rejected is your research hypothesis supported in many cases. That's confusing. But my point is, experiment is to generate this 1-bit information. Is your hypothesis supported or not supported? So this 1-0 information is the final product. For that purpose, we cannot say behavioral data is less important than EEG data, or EEG data is less important than fMRI data. fMRI data is less important than whatever. Because those measurements are all just serves for this 1-bit information generator as a dependent variable. And you cannot say one dependent variable is better than the other dependent variable. So if we say, oh, we use ICA or we use whatever this fancy EEG analysis method, that's why our conclusion is more important than yours. No, we cannot say that. As long as this experiment is designed properly and serves as a 1-bit information generator, then the dependent variable could be anything. That's why you can still write the science or nature paper by just using the reaction time. They are not even using any bio metric, but they just use the reaction time, and they can still publish Nature or Science. But once we start that kind of discussion, we tend to say, here I'm trying to criticize the ERP researchers, apparently. But if we start doing that, then we may miss many opportunities, particularly from the viewpoint of Silicon Valley guys. This, for example, this Elon Musk. For him, EEG data can be a treasure, and he can obtain many interesting things. And he's not looking at 1-bit information generation, because that's like, I'm not trying to say that's useless, okay? I would rather say the 1-bit information generating process is the basic of the science, okay? So this very solid firm step of confirmation of this 1-bit information is the most basic and most important thing for the science. But from the very different viewpoint, for example, even if you don't know anything about the brain, if you know how to use machine learning solution very smartly, then you may be able to obtain some result by skipping many of these cumbersome processes. And I would never deny that possibility. I even think that may find the next generation breakthrough. Who knows? So in order to allow such possibilities, and we want to get out of this cul-de-sac. So cul-de-sac is this kind of place. This road is closed, and there is even a statistics that these houses in the cul-de-sac is usually 20% more expensive than those houses outside the cul-de-sac. Why? Because the cul-de-sac is very comfortable. If you talk about what you know all the time, and if you don't make any like excursion, or you try to extend your knowledge or methods, then you stay in this cul-de-sac. And as you know, this dinosaur was stuck on this cul-de-sac, and they extinct, right? So that's the danger of sticking to one good method for too long time. And I think, in fact, it's somewhat problematic that nowadays the PhD student can still use the Steve Lux method, which was invented 50 years ago, and still get the PhD. And they of course ask the new questions, but their tools are completely the same as what they used 50 years ago. Even though we have such a powerful computers today, the memory space is now expanded from 16 bits to 32 bits, and now we use 64 bits. Why do we still stick to this limited analysis? And my mentor was definitely jumping out of this cul-de-sac. By no means I'm criticizing these guys in a meme way, but I have lots of respect to these guys, because using the ERP is still one of the most reliable methods for many of the clinical researchers and cognitive researchers as well. But this Scott Makeig's approach was using the very advanced signal processing to do something completely new, which can also verify what they have been doing from the very different context. So I'm not going to talk about the technical detail of the ICA here very much, but simply put, ICA is also known as a blind source separation, and this blind source separation take advantage of this central limit theorem. So central limit theorem simply means when signals are mixed, their probability density function gets fatter, which means the Gaussianity becomes increased. So more approaching more Gaussian when things are mixed. So if that's the principle, if you want to go reverse of this process, then unmixing means you find some non-Gaussian patterns. So you find some linear combination operation that makes each source activity maximally non-Gaussian. So that allows the unmixing. That sounds too simple, but in fact that is the principle. But what's interesting here is that This is the phenomenon in the time domain information, but in the context of the EEG analysis, what's so interesting is that when you solve this temporal problem, you also got the spatial solutions. These are not something we asked, but they automatically generate these biologically so plausible patterns. This is as if a single dipole generates here, this pattern or this pattern or that pattern. So this is a non-trivial coincidence. And Scott thought this is a proof that ICA, this math, meets the physiology. So that's like the natural blessing. So he decided to take advantage of this great nature of the ICA to the point that we have physiological backing, physiological interpretation by ICA. And our lab has been focusing on that process to show how ICA can obtain the physiological validity. And this is one great study showing that there are 20 variations of the independent component analysis, but when they reduce the mutual information, which is like how much, how effective the ICA is, more mutual information reduction, more dipolar scalp patterns. Dipolar means, these patterns. This is as if a single dipole generates this pattern. So there is a very interesting linear correlation between these two. So I want to quote the Arthur Clarke here. He said, any sufficiently advanced technology is indistinguishable from magic. So when we say, oh, ICA's work is magical, I truly believe that it's too good to be true. So I thought ICA may relate to the ground truth, because otherwise this is just too good to be true. By the way, oh, this is a part 3 summary. Okay, so I'm finishing soon, like in 1 minute. Part 3 summary, the EEG has been serving to the box models as a 1-bit information generator. So in that sense, whatever analysis is good, but if we indulge ourselves too much with such attitude, such a dismissive attitude to the new technologies, then we may get stuck in this cul-de-sac. So that's why I thought, studying the ICA is one good way to get out of this cul-de-sac, to do something more updated, more, reasonable in terms of this Silicon Valley guys. We can talk to Silicon Valley guys with no problem, because we not only study the physiology or EEG, but we also do signal processing, machine learning, so that's our advantage. So in my grand conclusion, so science is, after all, the process of the battles between the old dogma and the new dogma. And old dogma, I mean is a Popperian hypothesis-guided box models, and they're very protective, right? Their protection, the justification is all the dependent variables are equally important, and you cannot say ICA is more useful or better metrics than the others. But we want to make that new dogma, and we want to say no, ICA is better because X, Y, Z. So we want to show how such a defensive Popperianism can be overcome by our effort by using ICA. That's why I concluded ICA solution. That's the way to go. And ICA again means independent component analysis. But after 5 years, I have slightly different opinion, but still, it holds mostly. So that's my talk. Thank you very much.
Amazing. Thank you very much. That was great. I learned a lot myself. For example, I didn't know about the holes in the brain and how they can affect the EEG.
No, holes in the skull, not
in the skull.
brain.
Yeah, yeah. Thank you. Has anyone has any questions or would like to start with? Okay, I can start us with like a quick question about for the future. And I think you mentioned there was the poet that the soul of the poet can predict the
Predict
past
the
and
past and
remember the future.
Yeah, yeah.
What's the analogy from the
Okay,
talk?
sorry, I maybe skipped that part, right? Okay, let me get back, get it. Or maybe I didn't include that in this presentation slide, huh? Okay. Yeah, sorry, I missed that in this slide deck. That resonance pattern I showed you. So when you increase the, actually I've seen that when I was much younger, because one of my hobbies is an audio engineering. And audio engineering involves a lot of this vibration and how to control this vibration. So basically you want to vibrate the membrane, or the how do you call it, the plate, as accurate as possible. I mean, to the input signal. Okay, but if this diaphragm start to oscillate by its own, then that's the non-signal based oscillation, right? But such the resonance mode is not controlled by the input signal. We want to avoid such natural vibration happening, but we cannot escape from this natural vibration. That's why when you see the speaker system, you have big one and small ones, and sometimes you see a 1, 2, 3, right? That is because in the highest frequencies, your big plate oscillates in a really chaotic way, which is totally out of the control by the input signal. So in order to play the band limited the frequency signals, you have sometimes 2 ways or 3 ways. So basically the highest frequency is reproduced by the smallest diaphragm, because smallest diaphragm does not have such a the resonance mode in the highest frequency range. So this is called a, when the entire plate oscillates as a single rigid body plate, this is called a piston motion. So this is a piston motion. And when this resonance happens, then you are already out of the control. So that generates the distortion and stuff like that. So I learned these things as a hobby like 20 some years ago. And now this Paul Nunez is saying that this kind of resonance is actually happening in the real brain. And so that's like, oh, wait, I know this, I remember that. But now this resonance mode in the brain is gonna be my future EEG study. So that's like, I remember the future, right? And the predict the past is, just as I showed you, I thought in this way, and I found that this guy has already done that. And this guy gave me already a perfect answer some 10, 20 years ago by writing this book. So I made a prediction, and I actually found that was already answered by this guy. And I met this guy in person, and I enjoy afternoon discussion in the weekend with him. So I feel really satisfied, and I feel I could predict the past correctly. So I'm proud of that. And at the same time, I remembered the future in my audio hobby. So I have many hobbies, but this audio is really useful in my specialty. Audio and EEG have a lot in common.
I see. That's why you mentioned earlier your lab has a good link with music and audio. Yes.
Yeah, that's true. That's true. I also showed you that some guy brought the EEG research from East Coast to West Coast, right? Actually, that the connection of the people are all related to audio studies. So EEG research and audio research are really tightly connected. And those schools are from that East Coast guy. And also the Robert Galambos, who moved to the University of California. He is one of the originators of the auditory steady-state response studies and auditory brainstem responses. Because EEG has a really fast response, it's very suitable to study audio. And my mentor, Scott Makeig, he not only plays piano, violin, but he also composes. And his PhD was in music psychobiology.
Wow.
So there is a really strong tradition of sound and music. And I don't do the music part because I've never practiced musical instrument except for that xylophone. But I have been interested in audio technologies. I'm very obsessed by sound quality and mechanisms.
That's great, thank you. Ishan raised his hand for a question. Did you?
Yes, thank you, Aladdin. Can you hear me, Aladdin?
Yeah.
Oh, guys. Oh, okay. First of all, thank you very much for coming and giving lecture, Makoto. Thank you, especially because you're well known in the EEG lab community for sharing your pre-processing pipeline. And I used that when I came here.
Thank you.
Yeah, thank you so much, because what you presented, actually, I've been thinking about it. Like, for example, when you sort of like criticize about ERP, if we only limit ourselves, I'm coming from psychology background. As we know, most of psychologists or psychology researchers, they're only limited to such ERP paradigm. And I was thinking at the time I asked them, is this the way we look at the brain? They always keep saying, oh, this is what many researchers do this, then we have to follow this. But and now since I joined this lab, I don't work with psychologists, and it helps me to broaden my perspective until you come today, and then you confirm my sort of like questioning the way we look at the brain. Because if you only limit to such ERP or looking at the high amplitude and so on, we miss a lot of informations. So maybe you have any suggestions for EEG researcher or EEG student like me, what kind of way, a new way of looking at EEG data, so we can have a better understanding in order to, understand better about our brain.
So my practical advice is, if you have less than 64 channels, use ICA. If you have more than 64 channels, you may use ICA, but your main interest should be the high resolution EEG method proposed by Nunez and Srinivasan, these guys, which uses the spline Laplacian. And that belongs to another discussion, and I didn't go into that deeper here because I wanted to highlight more about ICA and this historical background and Scott Makeig. But again, if you have more than 64 channels, then you have an opportunity to do a real science. And the reason why I call it a real science is because even if you have more than 64 channels, actually you will not benefit from having that dense array electrode by using ICA, because ICA has a really strong dimension reduction effect. And as I showed you, for example, the principal component analysis compresses 56 channels data into 9 top components to explain 95%, blah, blah, blah. More or less the same happens. So I didn't show it today, but typically, you got 10 to 20 good brain independent components, however many electrodes you have. So even if you have 32 electrodes, then you got 32 independent components. If you have 64 electrodes, then you got 64 independent components, and 128 channels, 128 independent components. But in the end, what you need is the brain independent component. And there are many, like eye component, muscle component, heart component, etc., etc. If you collect all the good brain components, actually you got more or less the same number, something between 10 to 20. And the rest of the independent components are just junk. We don't even analyze them because, if you see this power spectrum densities, it's obviously those are junks. So what's the point of having 128 channels if you have only 10 to 20 independent components? So this is basically summarized by the Makoto's pessimism. Okay, but here is a solution, cure for the Makoto's pessimism, which is to use the spline Laplacian. If you use the spline Laplacian, you have to give up all the outermost line of the electrodes because they are not surrounded by other electrodes. Okay, but all the electrodes inside that outermost line is channel by channel thing is all independent in a sense. So if you have 128, maybe you have to give up 15 electrodes or something that is outermost. Okay, so you have the true degrees of the freedom of maybe 105 or something like that. But compared with 10 or 20 brain components, if you have 100 channels and every channel count, and every channel has an assumption that it is picking up the cortical activity right underneath the channel. So that's very simple, right? Simple but very effective. So if you have linearly increasing more number of the electrodes, then you have linearly increasing more spatial resolution. That's scientific, right? If you have more sensors, you have more data. So that science should work in this way. So that's our prediction works, and the spline Laplacian works in that exact way. That's why I'm saying if you have more than 64, and the reason why I'm saying 64 as this breaking point is that is actually discussed in this book, and I'm just giving you the conclusion. And if you want to know more, then I can discuss further in a different time. But yeah, so that's my answer, and hopefully my answer is clear.
Right. Thank you. Can I just ask one more question? As in Laplacians, I think because in the Laplacians the algorithm basically, that's one of the problem. That's why Laplacian comes. They try to disentangle these components which are mixed. One of the challenges as a new EEG student like me, if we use ICA component, because ICA components requires an experience to be able to interpret that component. So because in order to choose, maybe like for a new students, they don't know which component that I should choose. Maybe you have any tips after we use ICA and they give us, say, the first 10 important ICA components. Do you have any tips? How do we choose, the best way? Although maybe it may not be perfect, at least it helps us to learn, by the time to choose this properly. Okay. I think that's very important.
Yeah, that's a very good point. In using ICA, I never recently though, I never used my manual selection to pick up good brain ICs, but I always follow the result from the IC label. So if you see my wiki page, then I follow that recommended path. But you may need to see my Makoto's useful EEG lab code page, not like a pre-processing pipeline page, but useful EEG lab code page has a whole bunch of those good tricks, better tricks, if you know how to code using MATLAB. And by using IC label, it gives a probabilistic label, and I pick up any component that has the highest probability for the brain class. And if they have a brain class, and also their dipole is localized inside the brain, because if the dipole is outside the brain, that's out of the question, right? The dipole has to be inside the brain, and brain label, highest probability with the brain class, and also the residual variance from the dipole fitting. So I gave some explanation with figure, the definition of the residual variance. But basically, residual variance means how similar the ICA generated scalp topography is compared with the dipole fitted and its forward projected scalp patterns. So if you see my slides, then you will see it immediately. But if you want, I can show you now if you give me 1 minute. Do you want to see that?
Sure.
Okay. Let me see.
Oh, I think Kunal share it.
All right, let me share the screen. Am I sharing the screen successfully?
Yeah.
Good.
It's pre-processing, right?
Right, right.
Pipeline.
So this is the figure I'm talking about.
Okay.
Oops. It's gone. Yeah. So the residual variance is what residual from what? You know, that's a real question. And the Swartz Center guys never clearly explained what residual of what. You know, I found it kind of strange. So that's why I made this figure. So residual from the ideal dipole projection, you know, that's the residual. So when you compare this ICA generated scalp map and its dipole projection to the scalp, they're similar, right? So if you take the subtraction and compute the power of the residual variance, then you got 5%. So that's relatively small. Look at these two. These are kind of similar, but a single dipole cannot make this blue, red, blue pattern because it has only one dipole, and one dipole can make one red, one blue. So when there are two blues, then that's already out of the assumption of the dipolarity. Does that make sense? Right? Yeah. It's simple, right? So when you make the subtraction, then this is the result. And when you take the power across all the channels, then you got about 20% difference. And we kick this out because this is not dipolar. And this is the worst case, okay? In the left, this is the ICA generated scalp map, which is a mess. You know, with single dipole, as I said, you can get only one blue, one red, but how many blues do you have here? Like 7 or 8, right? And apparently 3 reds. And this is the best fitting single dipole, but it's only explaining this central red and all other things are missed. And this is the subtraction result. And the difference is about 77%. So that's like no way to include this as a brain. So dipolarity is also the measure of the physiological validity, because any source region, source activity inside the brain should be able to be modeled as a single dipole. Okay, so this physiological assumption is really trustable. So we don't need to worry about it. Okay, so anything dipolar inside the brain is physiologically, valid. And in this case, yes, this is a good independent component. We can say this decomposition is physiologically more valid compared with this or compared with that. So that's the residual variance. So I mentioned 3 methods, right? One is the IC label, and the other one is the residual variance, and the last one is the inside the brain. And all of those 3 methods were, let me see, how do I jump to the top? Maybe this window is not maximized, right? And let me jump to Makoto's useful AG lab code. Yes, thank you very much. This one. And ICA, too many ICAs. Right? Okay, this is IC label. Right, so this is how to perform component selection using IC label and the dipole information. So basically, you need to copy and paste for your code. So you need to know how to code in MATLAB. But I can give you a very simple explanation. Here, you run IC label. So this generates critical information of independent component. One is 76% brain and 12% muscle and stuff like that for all the independent components. So this takes care of that. Here, RV stands for residual variance. So that's, I told you, when you fit the dipoles, this residual variance is automatically generated. So I'm just checking if someone has larger than 15% of the residual variance, then that should be kicked out. And here I'm checking the inside the brain. So if the depth is larger than 1 centimeter from the scalp, I mean the brain surface, then that means dipole is floating in outside the brain, so that should be kicked out. So intersect of those three things. That means brain index from the IC level, good residual variance, and good inside the brain index. All the and, the Boolean and is taken to finally determine the independent component index. So this means that you don't need to be the super expert to use ICA, but you have to rely on those solutions. Although we still recommend that you educate yourself first, because otherwise you just become an end user of the system. And even if the system shows something really hugely wrong, you cannot tell. That's the problem, right? So researchers are not simple like end users of Windows or something, but you have to know what you're doing. And basic experience-based learning is still very important. If you think about how much effort and money, budget spent by those medical doctors, I collaborate with those neurologists, and they go to a summer camp, like 2 weeks summer camp, just to read the continuous data. And this is, I'm sorry to say this, but this is one of the most ridiculous thing, right? Because why don't you run FFT? Why don't you use this time frequency method? That was my initial impression. But now I have different opinion. It is very important for them to read the raw data, because raw data contains all the information. If you know how to read this, so as I said, if you have a theory-laden eyes, then you don't need to run FFT. You can make a very accurate prediction of what FFT results should show if you see this data. So that is the 2 weeks training of new theory-laden eyes. And their diagnosis based on raw EEG reading is extremely accurate and super trained. So this is a good example. So you have to educate yourself to some extent by data. So that's recommended.
Thank you so much. I'll in case I have a question, I'll get back to you. I need to look at your long code here in the MATLAB.
Yeah.
Thanks.
Thank you. We have a question from Tim.
Yeah, that's a great note. Thank you so much. So I think many of us are doing, virtual reality, mixed reality in the audience. So I just want to hear your view about. Now we are seeing many people putting even some sensors in the VR headsets, right? And there are lots of experiments around that. So the first one would be, what are the opportunities you see in these particular directions? Combining EEG or BCI with virtual or mixed reality. And also, when we are doing this type of experiments, what are the best practice to set up the whole things?
I see. What advantage, huh? I mean, outside the context of the EEG research, generally speaking, using the virtual reality is very, important technology. So in that general sense, using it in EEG research is, also important. I do have some, publications about such a VR application in EEG. But well, I can only make those very general comment on that point. And honestly, I don't like VR because as an experimenter, because it tends to generate less classical results. And I have a very strong longing for the physics rather than those applied studies. And if you think about this physics experiment, these things are really dumb simple. And I'm a person to look into such a simple phenomena and enjoy, simple but deep, this kind of thing is my favorite, and not like, oh, we did this, we did that using a Microsoft technology. It's like, maybe other guys can do it better than I do. I'm not very good at those super technology thing. I didn't even have a smartphone until recently.
Oh, okay.
I'm basically an anti-technology guy. But your second point, I think it definitely helps if you know the basics of the EEG, how the EEG signal is generated, and how it's volume conducted, and what is possible, what is not possible. Because in many BCI researches, with or without the VR technologies, in too many cases, they're asking about emotion, for example, or stress. Okay, and remember the fundamental EEG limitation number 1 was that EEG does not have sensitivity to this basal ganglia. But if you do this emotion experiment using fMRI, which region do you find first? Amygdala and there's basal ganglia. And we all miss that. And we may be able to find some reflection to that cortex, but that should be really weak. And I have never heard of such a convincing evidence of emotional detection or decoding using EEG. Although there are so many researchers saying, oh, we found this, we found that. But because I don't see very strong justification there. So that's why I typically give advice that, don't try to do everything, but you have a fixed menu. So doing EEG research is you go to the Indian restaurant, okay? And if you go to Indian restaurant and, I wanna have pasta, then that's like, maybe you wanna go to the different restaurant, If you go to the Indian restaurant, choose whatever they provide from their menu, and that's the best idea. And if you don't care what they provide, and if you make a claim that, I wanna eat spaghetti here, not curry, then they may be able to provide something like a spaghetti, but that's not their strength, right? And maybe they're even technically impossible to do something like emotion decoding or reward system, whatever. These things are all processed in the deep side of the brain, which EEG does not listen to. So this kind of basic guiding is always helpful. Right. And another thing is, you want to make your experimental design damn simple, as simple as possible. And this is always the key to the success. For example, if you want to ask the question X, okay, and how many conditions do you need? And if a student says, well, I want to use factorial design of 2 by 3 by 3, then I said, no, don't do that. Make your question into the form of 1 by 2, which is if this higher, A higher than B or B higher than A. And if the student says, no, I can't do that because blah, 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 then I would say, try to fit your question into this A or B style, because this is the key to the successful research, And all the experimental psychologists know this trick because they know how to use reaction time or hit rate analysis. Their weapons are really old and shabby, but they can always win the game. Why? Because they know how to design an experiment. They know how to design an experiment so that seemingly such a complex, high-level things can be beautifully answered just by measuring the reaction time. We have to pay very close attention to their skills and art. Then we realize how we can do this science better. Although I don't necessarily like the psychologist tricks all the time, because sometimes their skills are for the skills for the sake of the skills. So that's of course, any art can involve this kind of, art for the purpose of the art, this kind of convolved postmodern situations. But, making the damn simple design is really, really important. And if someone does not appreciate that fact, then, you should tell them very kindly and say that if you have 2 by 3 by 3, and you have a specific hypothesis in the interaction of those 3 factors, then you will probably lose this battle even before starting this fight. So that's the advice.
Right. No, but I mean, computational wise, because when we are doing this type of experiment, there's usually involve a lot of motions, right? Head motion, body movements. So computational wise, is there any technology that you suggest?
Computationally, it depends on your computational skill. If you know good engineers, you want to make good friends with them because they know lots of good methods and stuff. Sometimes MATLAB example codes are very helpful because they provide an excellent and guaranteed to work tutorials, so that studying those methods very closely always helps. But those technical things are like, that's an everyday thing for us. So of course you want to be as knowledgeable as possible, but it depends on your practice and your style and your collaborations and stuff like that. I know I'm not necessarily the super technical person. My PhD is in psychology, and I don't know that complicated math at all. I have only minimal skill sets to do my job.
Right. Thank you.
Thank you. We have 2 more questions if you have time.
Sure, I do.
Start with Yunhee.
Yes, please. Thank you, Makoto. My question is in line with Tim. So as he mentioned, we are researching in VR, AR. I mean, human behaviors in VR, AR, and we are planning to adopt this kind of mobile EEG setup. So my question is, have you any experience using this kind of mobile EEG? Because my concern is I can see some signals are recording using this kind of devices, but I'm not sure I'm correctly getting a noise-free EEG. So do you have any personal opinion using this kind of devices?
Okay, that's a very good question in the sense that that's generally difficult to say. To answer that question, I should admit that I have to use a lot of my experience to judge if some data is good or bad. That's why I told you, that you have to educate yourself first, because sometimes that is the only knowledge you can rely on. So, for example, I recently published a paper with some random guy from Romania, but interestingly, he got Fulbright scholarship, and he came to California, and I met him. He was only a random collaborator from Romania in the beginning. But anyways, he has this emotive data set. An emotive data set is not necessarily mobile, but it's a kind of simple, applied, low cost stuff. And he has a great hypothesis in the neuroeconomics and great design, blah blah blah. But when I saw the EEG data, oh my gosh, that was something is wrong with this data, and I can't even tell what is wrong. But all I can tell is that this is not right. When I see the power spectrum density, for example, if you want, I can show you his paper. I mean, he and I wrote it, but okay. I even discussed this issue in our past meetings, in the international conference. is this one? Let me share screen with you. Desktop to share, okay. So this is data. I don't know if you see what I saw, but when I see this plot, this is a power spectrum density. You know, typically you get it after running FFT on your data. For me, this is a really strange power spectrum density, which I have almost never seen. And again, I don't know if you have the same impression or not. If you don't, then I cannot explain why. It's just, you know, I can only refer to the fact that from my experience, you know, this is not right. And, you know, I cannot make myself distinguished from those medical doctors learning those, you know, the raw data, spending 2 weeks to see this is right, this is wrong, this is right, this is wrong. For me, this is wrong. And but I published it, right? So that's another question. But once you get this data, what can we do? You know, that's another question I needed to answer. And my conclusion was, if I cannot prove that this is 100% wrong, then I should leave it to other people to judge. You know what I mean? So even if you know, basically this is his data, not my data, and he wants to do something. So as a nice collaborator, you know, I want to help him to publish this no matter what, right? But I don't want to publish the bogus data. You know, that's the worst case ever. So I convinced myself by the fact that even if this data does not look entirely correct, okay, unless I'm convinced that this is entirely wrong, so this is a mixture of 0 and 1, maybe some part of the data is usable, some parts not. But as long as I mention that clearly in the limitation section, right, then this may be useful for some people, you know, even if I don't get convinced 100%. So sometimes you need to make this kind of compromisation. I think that's realistically necessary. And getting back to your original question, sometimes you can get a very clear answer to whether your data, recorded data, is good or not. You run FFT, okay? And if the power spectrum density more or less follows the 1/f curve, okay? So these are kind of following, but not exactly, right? The 1/f, maybe this cluster 16, this is more or less 1/f, or cluster 17, this is more or less 1/f. But other cases, this elbow is too deep. And for me, this is not like, you know, genuine EEG power spectrum density. But at least I'm not showing like non-1/f pattern. You know, they are still more or less 1/f. For example, if you see the power spectrum density of the muscle, then it's like a square root sign. It jumps up from here, and, you know, 20-30 hertz should show a plateau. So that's like a muscle, very clearly muscle. I don't see any muscle here. And some other patterns shows, you know, so from experience, I know, you know, this is not the type of any artifacts I know of, and somewhat closer to the brain patterns, but not exactly. So this is maybe the mixture of brain and something else, or even partially capturing the brain. And I don't know how good it is, so it's open. But before I judge, I just leave it to the readers. So as long as you clearly state it in the limitation section, or even in the introduction section, you can justify yourself by saying, oh, by the way, this is the experimental paradigm involving the body movement or whatever unconventional. Because of that, the data quality may be limited, but even given that, if you think about the significance of testing this, which has never been tested before, maybe this is still helpful to some part of the people in the field. You can make that justification, and I think that's still okay. I don't know if I answered your question.
Yeah, thank you for the answer.
Thank you. One last question by Kunal.
Thank you for the amazing and insightful talk, Makoto. As I think Tim and Yunhee already mentioned, and my question also aligned the similar line that we are working with VR as an applied research point of view. And so we right now, like as Yunhee shown the cap that we use, it's approximately like 16 channel or 32 channel. But then there are few headsets or devices that have come with only the frontal parietal region, like only this front part. And I remember you mentioning that it's better to remove the outer layer of the electrode, maybe for the analysis or to understand.
In the case of spline Laplacian.
Okay, not in.
No, I'm not. That's not like general comments. Okay, spline Laplacian is basically the same as edge detection in image processing. So in order to perform the edge detection, some pixel must be surrounded by other pixels, right? And actually edge detection uses some kind of Laplacian, but when this pixel is not surrounded by other pixels, then you cannot take the difference. That's why that's causes a problem. So that's why I mentioned that.
Oh yeah, I mean, but in general, like my question is about like whether this particular part, like using this frontal parietal, and as a VR device where you have motion and people are interacting, the researchers are trying to investigate if we can determine like cognitive load, stress, or maybe emotion. And I might be asking for a pasta.
I mean,
to be
traumatized.
yeah, I know. To be honest, my research, my PhD is about emotion recognition in virtual reality. So
congratulations.
that's why I went to Indian restaurant and asked for maybe like a different recipe. But yeah, so I mean, yeah, again, this is a dilemma I'm still in, whether EEG or wearable EEG would be able to do that. But then there are a lot of machine learning, like whatever research people have tried with maybe deep data set where they have shown emotional videos and recorded their EEG and tried the machine learning like pattern recognition thingy approach. So what's your thought of using just the frontal part or whatever thing, but then train the models to get emotional, like whatever data we get, and then we try to recognize the pattern and use that information in some way, like maybe to adapt the VR to give a real-time biofeedback or something. So
okay, so first I want to clarify my standpoint. Okay, I stand on the point that I support the classical science approach. Okay, and basically that means I declare war against the the machine learning users approach who does not care the basic science, and they believe they can make a big jump to go to the better conclusion. So that is indeed the strength of using the deep learning, right? You don't need to know the nature of the data, but machine learns it, and as long as you know how to use that machine, not the data, then you can do something great. So that's okay. So that's the two different dogmas works. So as my conclusion part mentioned, the advancement of the science is basically the fight against those different dogmas, right? And I would say, we scientists should take these solid approaches and solid steps, and maybe other more engineering minded Silicon Valley guys would say, all those old stonehead scientists, they're useless. Their methods are same as 100 years ago. We can use machine learning to do the better job. Who is correct? Who is winning? only the result can show. If they publish a Nature or Science paper showing that, oh, our machine learning method can, demystify the consciousness, then yeah, they won. But until this is, who is the winner is determined, we are constantly fighting. And if you say you are from the machine learning team and you want to do the machine learning and whatever scientific baseline there, I will use 16 channel system to decode the emotion, yeah, go ahead. And if you can prove it, you win. And if you can't prove it, well, that does not mean I win, but that the winner is not determined at that point. So it's the same as evolutionary science, right? If some species have a new weapon to survive and reproduce, the proof is, in 100 generations after, is that specific property prevailing or not? So we are all, making that bet. So in that sense, and from the scientific viewpoint, if you ask, so it's low number of the electrodes around here, practically, okay. My personal recommendation is you have to cover the whole brain as even as possible, because so that you can maximize the probability of picking up, good noiseless, not noiseless, but less noise, EEG signal from around the head. And particularly this central part of the head is always the signal is clean. So if you don't put the electrodes here, you're missing the good part of the EEG, generally speaking, right? And this peripheral part, lots of muscles and eyes and, these facial muscles, it's basically bad. You have more chance to get whatever this artifact. So it's probably, if I were I would concentrate on this, this top part of the brain, which is far from the muscle thing. And if you have 16, probably you got more or less okay coverage. So that I would recommend. There is a 1020 system montage that uses 19 channels, but you may give up 3 channels.
Yeah, so we have OpenBCI EEG cap. The resolution and the data consistency is not that great, but then at least it's giving some information of the FP1, FP2, and then frontal region, occipital region, and parietal and cerebral. So I'm assuming if we have that kind of information, at least we should be able to interpret it into something. But then, as you know, in VR we have a lot of motion. So in the psychology studies, we have to keep the person's chin at the chin rest and then just monitor that. But like, I find it very difficult, and it's a major question in the physiology in HCI research, especially like in the BCI studies. How do you reduce the motion artifact? Like, we try to keep the person during the experiment, we try to keep him as calm as possible and as stable as possible, but we can't ask them to stop interacting with the environment. Otherwise, we won't understand the behavior. So do you think those noises can actually manipulate a lot of data and create a bad data set if we don't remove it?
Yeah, I think that's entirely possible. In fact, one of my collaborators told me that he does a BCI of the aviation, the pilot, and BCI on the aviation is very much expected, and they got big grant and stuff. But in his opinion, okay, in previous BCI research on aviation is all decoding the muscle, facial muscle. That's why it has a really high accuracy, and that is something laughable for him. But from other viewpoint, if whatever works, it's working. I don't wanna do that for my own research, because I want to study brain. So in that case, the best thing is when you record the data, then you try to minimize the artifact. But if that's inevitable, actually I have a project of 3-ball jugglings So EEG during the 3-ball jugglings to analyze. What can we do? We cannot suppress the motion because this is a source of the brain activity as well. So we are improving the signal processing to remove the artifact, although we are not sure if that works. But in such an extreme case, we have to switch our way of thinking to the better than nothing mindset. So if something is better than random chance, then that's usable, So that's a complete switch of the mindset, and it's very humiliating, but sometimes we have to do that.
As long as we are publishing. Yeah, thank you very much for your inputs and really amazing presentation. Thank you.
Thank you, Kunal. One last, I know we said one last, but this is definitely the last one. Rio.
Sorry for one last question. Konnichiwa. Thank you so much for your presentation, Makoto-san. It was really nice, and I learned a lot, as well as other students here. And also very happy to see someone from my hometown, same hometown, working on this crazy research, Osaka.
Oh, okay.
That's so it's pretty fun to hear all your journey came through. So I'm a research engineer here. So I do more like hardware, software engineering, and then I help some people's research here. And I have a small answer from on your like power spectrum, wondering that some of those like a modern sensor system has no enough power filtering. Power noise filtering circuit on the hardware, so that I recently came to know that they get some random noise from either power line or some facial muscles around the face. So that could be one clue for those random noise you see in the power spectrum. But anyways, I have a question on the some applied science and applied science part of those EEG research. Of course I understand you are not very interested in those parts, those on the application side of those EEG research projects. But I'm just wondering, as a HCI researcher, like, have you ever came across any interesting HCI or like brain computers interface research projects that was quite interesting for you, or like, yeah, have you ever seen anything interesting?
Yes. I have a great answer for you. I listened to my colleague's presentation a few weeks ago, and he was talking about the BCI, and that was really convincing. And actually, I found that was one of the best BCI presentation ever. So my recommendation is you invite my colleague for the next presentation. Because no, seriously, his presentation was really impressive, and I actually thought, that was more than I expected. So I totally renewed my evaluation of his, achievement and his ability to communicate. So that was really great stuff. So I highly recommend you invite him for the next talk.
What's his name, or the paper, or the talk?
Masaki Nakanishi. I don't think he's from Osaka, but he's a Japanese. Masaki. So you can find his name in the Swartz Center, this research scientist track.
Well, out of curiosity, as you mentioned, your hobby is music and audio. So have you tried applying, again, you're not interested in applying EEG in some ways, but then have you tried like maybe creating music with EEG or something? I mean, there are a lot of things available, but just like for fun, maybe like as you shown the image of that resonating thing.
Yeah. My colleagues did that. Like they even did, sorry, fighter jet is flying, so maybe noisy. But the chamber orchestra with violin, cello, flute, and brain. Wow. So brain is of course BCI, and this guy tries to remember some emotional state, and that so that it changes the EEG wave, and that EEG wave is modulated and transposed to make some audible sound. So that chamber music with brainist, that was like 10 years ago he did. Generally speaking, I don't think those things are super interesting because you can make any sound. For example, if I put my electrode in the muscle, and when I move my hand, then that generates muscle, this signal. I can make sound or music, if you want to call it, from that muscle movement. But that's not very interesting. And for me, the brain is not that mysterious thing anymore. If you think, then your brain works. What's so mysterious? Brain is not that different from this hand. It follows its own rule, of course, but and it's maybe more complicated, more than this hand. But and the bottom line is, it's still a thing. If you hit it, it makes a resonance, and So well, this is of course my very personal opinion, but most of these PCI-based semi-artistic, brain music or brain art is mostly not very interesting for me, because probably they have a very naive thinking that anything from the brain is mysterious. So they have to be demystified first. But, because they think, oh, brain is so complicated and mysterious, and this demystifying something is very important, but very difficult. As the philosopher Immanuel Kant said, the duty of the philosophy is to reject any wrong imaginations that arise from the misunderstandings. So in other words, they have lots of potential misunderstandings about the brain. That's why they think brain is so mysterious and mystery. But no, brain is not that mysterious. So they are just taking advantage of that mysteriousness of the brain. So that's my dismissive opinion.
Thank you for your opinion.
Thank you very much. I have to conclude this talk. Thank you for everyone who attended this seminar series. If you have any questions later, please let me know, and then I will pass them to Makoto. Thank you, Makoto, for joining us.
You're welcome. I also enjoyed the discussion with you guys.
Really appreciate it.
So nice. I like you guys very much.
We like you too. And if there's any opportunity in the future to work or collaborate together, or even if you visit New Zealand, please let us know. We'd love to host you here and show you what we're working on.
Yeah.
That's nice. Thank you. I'm very happy to hear that.
Thank you very much.
Thank you so much, Makoto.
You're welcome. Bye.
Bye.